to this year's Buhl lecture. I know people will be coming on in, so take your time. I thought we'd sort of slowly get started here. I'd like to begin by introducing our extraordinary dean, Fred Gilman, who's going to be introducing and talking about today's speaker. Fred is many things of relevance to this lecture. Besides being our dean, he was head of the physics department. He was 22 years at Stanford before that, with a brief interlude for the superconducting super collider. He also serves as the Buhl professor. And so who would be more appropriate to introduce today's Buhl speaker? Fred?
Okay, thank you, Mark. And as Buhl Professor of Theoretical Physics, I'm very pleased to welcome you to the 2012 Buhl Lecture. This is the 17th Buhl Lecture since the series was reinstituted in '96. And we're very pleased to have Daniel Eisenstein at Carnegie Mellon today to give this year's Buhl Lecture. Daniel, in fact, spent his early years in Pittsburgh. He could be almost considered a Pittsburgher, since his father, Bob Eisenstein, an old friend of mine and of many others who are in the audience, since his father, Bob Eisenstein, was a physics professor at Carnegie Mellon. Daniel, Princeton undergrad, went on to get his PhD at Harvard with Avi Loeb as his thesis advisor, and then there followed postdoctoral positions at the Institute for Advanced Study and the University of Chicago. After that, he was, for I think it's 9 years, on the University of Arizona astronomy faculty, and then finally he went back to Harvard in 2010. While trained as a theorist, Daniel has made great contributions to cosmology with a mix of theoretical and observational methods. And in particular, on the observational side, he's been the prime mover in the Sloan Digital Sky Survey since the late 90s, and now he's the director of the third phase of what's called SDSS-III, after it, for the third phase, SDSS-III. His focus has been in developing and implementing a new standard yardstick to measure cosmological distances, Baryon acoustic oscillations. Sounds very impressive, and you can learn today much about that. And using it then to make precise measurements of the accelerating expansion of the universe, driven by, for want of any other idea or name, what we call dark energy. So it gives me great pleasure to introduce the 2012 Buhl lecturer, Daniel Eisenstein, who will be speaking on his work on dark energy and cosmic sound. Daniel?
Well, it is a great pleasure to be here today to tell you some about the work that we've been doing to study the properties of dark energy. And I have many collaborators to thank, but also work throughout the Sloan Digital Sky Survey. It's not a little bit. But of course, it is really also a great pleasure because it's a bit of a homecoming for me, having grown up in Pittsburgh through elementary school and middle school. And I actually, just to get started, dug up this picture of me in my father's office in Wien Hall. You can tell it's Wien Hall by the size of the cinder block. And I seem to be engaged in some early math exercise here, so it's all good foreshadowing of what was to come. So I'm going to be telling you today about recent work in cosmology and in the study of dark energy. And I'll be focusing here on the study of something called the Baryon Acoustic Oscillations. I hope that will become very clear to you what that means as we go through, and how we can use them to measure the cosmic distance scale. And I'll then take you through a tour of how we actually do these large projects with the Sloan Digital Sky Survey, and then show you some of the measurements that we've made from that and what we've learned about cosmology. So to get started, let's focus in just on what the big question of the talk is, which is what is the universe made of? And of course, what we found is that the composition of the universe turns out to have a very surprising answer, and really the kind of stuff that we're all made of, protons and neutrons and electrons, only makes up a very small fraction of the overall universe, and there's lots of other stuff going on. So the first thing that was discovered, which actually has its earliest seeds back to the 30s, but really became much more known to people in the 1970s, is this idea of dark matter. So this came about from the fact that when you look at, on the scales of galaxies, how fast galaxies are rotating, or how fast galaxies are moving inside bigger clusters of galaxies, the motions that we measure are too large to be bound into the system if the system has the mass that we observe in the stars. So the stars do not exert enough gravitational force to keep the galaxies in a simple rotation. And so we inferred there must be extra mass. And moreover, work in the past 40 years has shown that this extra mass is not just more of the normal stuff, more of protons and neutrons and electrons. It's actually some new exotic form of matter that, frankly, we're still looking to try to figure out what it is. So having discovered that there's this extra mass in galaxies and in clusters of galaxies, one then wants to try to figure out how much there is in the universe as a whole. And in the same way that we used motions of stuff to infer motions inside galaxies to infer dark matter in galaxies, or motions inside clusters of galaxies to get the amount of matter in there, we want to use motions on larger and larger scales in order to infer how much material is around in the galaxy. And this is very challenging because it's very hard to measure things on large scales. And there's basically two different versions of this. One is to measure on scales of superclusters, go out even further and try to measure how the superclusters are moving around, and that has been done and gives an answer. But what I'm going to be focusing on here is trying to measure the effect of gravity on the universe as a whole. You know, that the universe is expanding, and the rate at which that expansion is being changed is indicating how much material is flowing around. So I mentioned the expanding universe, and that's been known since the 1920s, but at the same time, a lot of people don't have a very clear sense of it. And the idea here is that we're using Doppler shifts to measure how fast galaxies are moving away from us. And I just thought it'd be fun to give you an example of these Doppler shifts. So these are spectra of galaxies. This is wavelength running from blue light out to, orange light, red light, and then off into the infrared. And you can see this is the spectrum of light that comes from a galaxy. And there's this characteristic double notch feature here, which you can see here, and then here, and then here, and then here, and then here. And this is all just the effect of these galaxies moving faster and faster away from us, and the light being redshifted by the Doppler shift. And we find that the rate at which the galaxies are moving away from us is approximately proportional to the distance that the galaxy is away from us. And this is known as the Hubble relation, a famous relation in astronomy. So I'm going to be talking a lot about redshifts here, and I just wanted to remind people that this redshift is, it is this recessional velocity. And the reason that we like to talk about redshift is that the things that are at higher redshift are moving away from us faster, and that means they are more distant, and that means that the light has taken longer to travel from that object to us. So when I talk about redshift, really what I'm talking about is some previous epoch in the universe. So astronomers, we use redshift as a label of time in addition to its direct measurable thing, which is the Doppler shift. So let's see how we can map from distances to try to determine acceleration. So if the universe was just, got some initial start and just coasted on inertial motion, then you would predict that the size of the universe would be increasing linearly with time. This would just be a bulk expansion of the universe, no gravity, nothing acting on it. And so we would be here at the present day and at the present size. And as you move back in time, we would be measuring, here's redshift 0, and then here's redshift 1, where the universe is half its size, and that would be some amount of time back in the past. But instead, if you think that the universe is slowing down over time because gravity is pulling on things, if you start off with some faster expansion, then gravity should pull and things should slow down, you would get a curve like this, and you would see that the universe would be younger, it would not be as old. And in particular, the amount of time that it would take to look back to a given redshift, say when the universe is half its size, would be less, and so the objects would appear a little bit closer and a little bit brighter. So this gives you the idea that you can actually try to measure how much deceleration, how much matter is in the universe by just going out to objects of a given redshift and trying to measure how far away they are. If they're further away, then there must be less matter in the universe. And so this brought us to the idea of doing this with supernovae. And the reason we want to use supernovae is that we think that they basically that they have more or less a single luminosity. So you basically can infer how far away something is by measuring the flux that you receive from the object. If I stand here with a 100-watt light bulb, you can measure how much flux is coming from that light bulb, and you would infer a distance. And if I then step further away, it would get fainter because of the inverse square law, and you would measure less flux, and you could measure the relative distances. So when people went out to do this, they found a great surprise, which is that the high redshift supernovae were too faint. And it's not only that they were sort of too faint to match to any deceleration, it's that they actually overshot. They were really too faint. And this indicated that the universe actually had to be accelerating. And remarkably, two different teams found similar results. And of course, that resulted in the Nobel Prize in Physics this past year, given out to Adam Rees, Brian Schmidt, and Saul Perlmutter. So here's how you can see that in the plot that I showed before, that basically, if you have an early deceleration, but then recent acceleration, then you have more time and hence more distance to look back to a given redshift. So that's the key idea here, that by measuring distances very accurately, you can try to figure out how much the universe is accelerating or decelerating. So both these teams found that there was, evidence for an accelerating expansion rate, and it's really a remarkable discovery that we now think that we live in a universe where most of the stuff in the universe is this dark energy stuff that's responsible for the acceleration of the universe. The dark matter is here, and all the normal protons and neutrons are just filling up 4% of the pie chart. And in fact, the stuff that we really think about, the stars, are actually less than 1%. And the stuff that we're made of, mostly heavy elements, things heavier than hydrogen, helium, is way less than 0.1%. So we're really a tiny sliver of the overall universe. And of course, that leads us to the big question from a cosmology point of view of, what is this dark matter and what is this dark energy? So as regards dark energy, many possible explanations have been advanced. Of course, the most famous one goes back to Einstein, this idea of a cosmological constant. But there's lots of other ideas. There's ideas that there might be a new force of nature. There's ideas that maybe gravity, we don't understand gravity somehow, and really gravity, instead of just pulling on things, as we of course all know that it should, that maybe on the largest scales it actually is pushing stuff away. Or maybe it's that we don't live in 3 dimensions, we actually live in 10 dimensions, as string theory would say, and the gravity is functioning different because of that. Or, you can go on and on and on, and there's many, many feet of library shelves that have been consumed with trying to understand what this might be. And I think it's fair to say that all these ideas are exotic, and none of them are so aesthetically compelling as to be the obvious preference. And so we're led to the question of how can we distinguish between these observationally? And the path that we're going to be talking about here is how to get distances measured better and better, to try to really refine the measurement of those distances so that we can figure out if this dark energy is actually constant in time, like the cosmological constant would predict, or if it's doing something else. So earlier I talked about the supernovae, which were a method where you have an object of a standard luminosity, like a 100-watt light bulb, and you're moving that away and inferring distance from looking at the relative flux. But here we're actually going to be talking about an object of a given size. And the main thesis for the talk is that sound waves in the early universe imprint a signature into the clustering of galaxies that encodes a particular length scale. And I'll go through that statement in quite a lot of detail in the next 15 minutes. But let's just imagine that I give a standard length scale. I tell you I am 6'2". Well, you can then take out, you can infer from the angle that you see how far away I am from you. The people in the front row think that I subtend a big angle. The people in the back row think that I subtend a much smaller angle, and we can, by comparing their angular measurements, they would be able to determine what the relative distances are. And if we really told them that I was 6'3", then anybody in the audience would be able to figure out from the angle exactly how far they are away. So that's the idea of a standard ruler. And the phenomena of these sound waves is known as the Baryon Acoustic Oscillations, BAO. I'll write that in a couple slides. But this basic idea is just we're trying to measure distance by having an object of known size. OK, so the story of the acoustic oscillations begins with the cosmic microwave background. And the cosmic microwave background is radiation that's bathing us. It's only 3 degrees above absolute zero, but it's radiation from the very earliest time in the universe. It's the relic heat that's left over from the Big Bang. And of course, the wonderful thing about the microwave background is that when we look out at it, we are actually looking back into the early universe. Very few of the microwave background photons get scattered on, as they travel through the recent universe. So when we look at the microwave background, we're actually looking at a picture of the universe only about 400,000 years after the Big Bang. So we really can see a baby picture of the universe. And unlike the picture that I showed you in the second slide, this picture is much more boring. There's basically, it's the same in all directions. The microwave background is incredibly smooth. Well, people saw that and they said, well, we should make better and better measurements to try to see if we can see any early variations in the microwave background. And they looked and looked, and by turning up the contrast by a part in 1,000, so this is 3 Kelvin above 3 degrees above absolute zero, and now this is looking at the 3 millikelvin variations, and they start to see a dipole signature in the sky. The microwave background is a part in 1,000 hotter in that direction than it is in this direction. And this is actually caused by the motion of the Earth relative to the microwave background. So it's a Doppler shift itself. We're moving, and in the direction that we're moving, the microwave background looks a little hotter. OK, so that was a first discovery. But by itself, it didn't tell us very much except for how fast we were moving relative to this smooth heat bath. So they kept looking. And in 1992, the COBE mission announced its discovery of perturbations in the microwave background at a part in 100,000. So this is really a crucial picture in the development of cosmology. This is a picture of the tiny density perturbations in the early universe, only a part in 100,000 type of perturbations, but on gigantic scales. And we're looking out back to this very early time. So this was a wonderful discovery and prompted the development of a second satellite called the WMAP satellite, which achieved much better resolution. And so now we're seeing a great deal of structure in the early universe. Really a wonderful discovery. So when you look at this picture, you can see fluctuations in the temperature. And I should say, again, these are just parts of the sky that are slightly hotter or slightly colder relative to the 3-degree background. So when you look at this picture, you can see some fluctuations on very large scales, some fluctuations on very small scales. But when you look carefully, you see there's a characteristic scale. If I just blow up a part of this picture and you look at it, your eye is drawn to these hot and cold spots that are all about the same size. Things about this size, about that size, about that size. There's just a characteristic size of the fluctuations on this map, which is about ½ a degree. So patches of the sky about ½ a degree in size tend to be correlated to either be a little bit high in temperature or a little bit low in temperature. And this is the result of these sound waves in the early universe. So when we try to analyze this map statistically, we break it up and we consider how much fluctuations there are on large scales and how much on intermediate scales and how much on small scales, as if we were taking the picture here and breaking it up into a set of frequencies, like playing the piano keys. Like how hard do you want to hit middle C compared to a high A or a low E? And you get to a graph like this, where this is large scales and this is small scales, and the amount of fluctuations here are telling you how much amplitude there is in the modes of that scale. And you see this big bump at 1 degree scale. These are the acoustic oscillations, and you see harmonics after that. And if you think that this slide is slightly impressionistic about harmonics, then this is the most recent data where you can go 1, 2, 3, 4, 5, 6, 7, 8, and maybe you believe the 9th harmonic here. So this is really like you're playing a violin string, and instead of just getting the fundamental mode, you're getting the fundamental mode and the first overtone and the second overtone and on to the 8th overtone of these oscillations that happen in the early universe. Okay, so what is going on? Why are we getting oscillations in the early universe? Well, the key epoch here is this epoch called recombination, which is, in redshift language is redshift of 1,000. That means the universe was 1,000 times smaller than that it is today. That means it's 1 billion times denser and 1,000 times hotter. So today the temperature is about 3 Kelvin. Back then the temperature was about 3,000 Kelvin. And this is an epoch about 400,000 years after the Big Bang. Now the reason that this is such an important time in cosmology is because that early universe, being hotter and denser, is sufficiently hot and dense that prior to this time, all of the electrons were stripped off of the nuclei. So instead of having atomic hydrogen and atomic helium, you have ionized hydrogen. You have bare protons, bare helium nuclei, and all of the electrons that go along with them. So the universe is ionized. And this is very important because when you have an ionized medium and you try to send photons, light, through that medium, it gets scattered. The photons get scattered. And the reason this is then so important is that if you take a packet of this plasma and you compress it, say by the force of gravity, the photons are trapped inside this compressing region. And as the walls close in, the photons are getting scattered higher and higher in energy, and they will eventually generate more and more radiation pressure. So you take this packet of plasma and you're squeezing it, and the pressure is increasing. And of course, you can't do that forever. As you increase the pressure, eventually the pressure tries to push back. It'll push back out, overshoot, and then that part of the universe becomes too cold, at which point the rest of the universe pushes back on it. So at these early times, the fact that the universe is ionized and filled with the early microwave background radiation causes all the perturbations in the universe to oscillate like sound waves. So it's really like the sound waves traveling in this room. The difference is that in this room, the sound waves are a pressure wave that's supported by the random motion of the air molecules. When you have a compression, sound waves are alternating compression and rarefaction in a fluid, and as you compress, the air heats up and it actually pushes back and causes an expansion. And here, the random motion is not of the gas particles, it's actually by the photons of the microwave background. After recombination, the universe becomes neutral. Now photons can travel great distances. Again, just like the gas in this room is neutral, and that's why you can see me and I can see you. If the gas in this room were ionized, we wouldn't actually be seeing each other. It would just be a fog. And so now the photons can travel freely. If you take some of the part of the region and you squeeze it by gravity, the photons leave, and you have more and more gravity, and it's just pulling all the way in, and you get a runaway instability to get more and more structure formed. So you have this very major transition in the early universe where perturbations are stable because they're oscillating as sound waves to a situation where the perturbations are unstable and they're growing by this gravitational collapse. So let's see what this does for us. So now let's imagine a universe that's smooth everywhere except for one little region. And in this region, it's overdense, initially overdense. And because it's overdense, it's also overpressured. And that overpressure tries to equilibrate by driving a spherical sound wave out into the ambient medium. That wave travels out at the speed of sound, which happens to be 57% of the speed of light. The radiation pressure in the early universe is really, really strong, and it pushes the gas wherever it wants to go. And the result is that everything moves relativistically. So you have this perturbation sprinting outwards at 57% of the speed of light, and it will travel, the wave travels until you get to the epoch of recombination. At the epoch of recombination, the photons leave, the sound speed in the gas plummets, and the wave basically gets frozen in at a radius that today is about 500 million light years. So basically you get this very rapid expansion. So now we're left with overdensity in the center from the original perturbation in the dark matter, overdensity in this ring of 500 million light years, which is from the gas, and both of these regions will now spur gravitational instability, and they will both preferentially form galaxies. And so when we look to see galaxies today, we will preferentially see galaxies, pairs of galaxies that are separated by this distance of 500 million light years. If there's a region that's going to be that's going to be good at forming galaxies here, it will have emitted a spherical sound wave which will have traveled out and created a slight excess of probability to have a galaxy way over here. And it's that pairwise separation of galaxies that is going to give us the signal we want to look for. Now, although the last picture sort of you could see this nice ripple in a pond going outwards, really the universe was perturbed everywhere initially, and so every region has thrown off its spherical sound wave, and you get this background of stuff that you've got to try to understand. And so you don't get to see like little bullseye patterns in the galaxy distribution. It's not that you get to see little rings in the sky. What you're going to be looking for is this small excess of correlation that pairs of galaxies are slightly more likely to be separated by 500 million light years than they are by 400 or 600 million light years. So there's a very small amplification at that scale. So I'll just show you this again now with the calculation, a more accurate calculation. And so this is radius in units that are expanding with the scale of the universe. And here is perturbation that's starting off at 0 radius. And we'll just run this forwards. There's actually 4 lines here. There's dark matter, gas and photons, which are linked together, and neutrinos. And these gas and photons are sprinting out from this initial central source. And now we're getting to the epoch of recombination. The photons are beginning to separate away from the gas. The dark matter is still here at the center. Now the photons will spread themselves thin. And so now we're left with dark matter in the center and this gas at this ring of 500 million light years. And now this gas will attract dark matter, this dark matter will attract gas, and the two will come back into lockstep as you go down towards today. So now we would preferentially form galaxies in the center and galaxies in this ring, and that's the key signature that we're looking for. Okay, so why is this so useful for us? Well, it's because this distance of 500 million light years is a very easy calculation. It's just the distance that the sound waves could travel in the early universe. And basically, how far something can travel just depends upon its velocity and the amount of time it has to travel. So really, the basic point is just multiply the velocity by the time. So in detail, you've got to figure out how fast things are moving. That depends upon the amount of inertia in the fluid, which depends upon the ratio of baryons to photons. And you need to know how long it takes to propagate, and I'm not going to go into it, but that depends upon how much matter there is in the universe compared to how much radiation. But once you know these two quantities, you can compute exactly how far this sound wave traveled. And the wonderful thing is that the microwave background anisotropies, the relative heights of those peaks and troughs that I showed you in the earlier spectrum, allow us to infer exactly these quantities and to predict this scale. So today we know this scale to about 1% from the WMAP data. So basically the early universe has given us a characteristic pattern in the clustering of galaxies whose scale we know to 1%. So basically the universe has told us how tall I am to about 1% accuracy, about 1 inch. Right, 6.6 feet 2 inches plus or minus 1 inch. And that's a wonderful thing. Normally in cosmology, we're always caught with the problem that we look out at galaxies and we can't decide how far away they are because we don't know if it's a really big galaxy that's far away or a really small galaxy that's nearby. We're always trapped in trying to figure out how distant things are. But in this case, we actually have something whose size we really know. So when we go out to measure it in a redshift survey, we can measure it along the line of sight or across the line of sight. And along the line of sight will give us a difference in the redshift, which is related to something called the Hubble parameter. Across the line of sight will give us a difference in angle that's related to something called the angular diameter distance, and so we can measure these two quantities. And that really is exactly related to measuring the cosmological distance scale. Okay, so we started doing this in our first detection in 2005. This was data from the SDSS, which I'll describe here in a minute, but this was this is now co-moving separation, so this is 500 million light years here, and this is our data with this little amplitude, bump in amplitude in the clustering at the 500 million light year scale, and overlaid with some theories. And basically, if the theories, if we had measured the distance, if we had used the wrong distance to do the measurements, if all of our distances had been a factor of 2 too large, then the data would have the peak would have appeared over here and would not have matched up with the theory. So basically, the fact that the theory agrees with the where the bump is in the data is telling us that our distance, the distance we were using, was about right. And so this gave us a 4% measurement of the distance to redshift 0.35, which was at the time was the most accurate extragalactic distance that had been measured. Okay, so just to wrap up this part of the talk, I mean, the virtue of this method is that this signature is created by physics in the early universe. The perturbations are really small. We can do the calculations really well. And so we really can predict this distance scale to 1%. We then get to measure it, and we can measure it in lots of different places and at different redshifts. And in doing so, we're constructing the cosmological distance scale using big angles on the sky, big differences in redshifts. So it's a relatively straightforward thing to do. This preferred length scale of 500 million light years is a very large scale. And so although at small scales in the formation of galaxies and clusters, it's a very astrophysics can be very complicated. On these very large scales, astrophysics turns out to be much simpler. And we really don't know a way to try to mess up this scale. So it's a really excellent method from all these points of view. You get very robust distance measurements out of it. The problem is that you need a lot of data. It's a very large scale, and so it's very challenging to go out and collect the data that you need to actually detect this. So how do we go about trying to do this? Well, we're trying to map the universe, and we're trying to make a three-dimensional map of the clustering of matter. And we do this by galaxy redshift surveys. So we're basically trying to measure the positions of galaxies on the sky. That gives us a two-dimensional map. And then we're going to take spectra of these galaxies to measure the redshift and thereby infer the distance. And once you have an angle and a distance, then you've really set down the three-dimensional position of the object. And unfortunately, because this scale is very large, we really need to map enormous volumes of the universe. So we're talking about volumes that are a few billion light years on a side, and you need to trace those out with of order 1 million galaxies. So it's a very big data problem to try to go out and to gather the data to do this. Okay, so that brings us to the Sloan Digital Sky Survey. So the SDSS is the world's largest galaxy redshift survey. The project actually began in 1990, so it's been going on for 22 years. I joined the project in 1998, about the time that it was starting to take data. And the project really consists of two different parts. The first is taking a picture of the sky to make a really accurate map of where the galaxies are, in terms of where they are on the sky, angularly. And that resulted in digital pictures of 1/3 of the sky, and actually 5 different colors, and cataloging about 500 million objects. And then we performed spectroscopy of about 1.5 million of those objects, mostly galaxies. And we finished that in 2008. And I'll tell you more about what we've been doing since 2008 later on. But I just wanted to give you a feel for this, how the project works. This is the telescope that we use. It's in Apache Point, New Mexico, above Alamogordo, about 9,000 feet elevation. And by the standards of astronomy now, this is a relatively modest-sized telescope. It's about 2.5 meters in primary aperture. The primary mirror's right there. So it's about 8 feet across, which is relatively small compared to the really big telescopes that are around, which are more of order 30 feet across. But what makes this telescope special is that the field of view is very large. So those telescopes have a tiny, tiny field of view. This telescope has a field of view which is about 3 degrees. So, not as big as your binoculars, but still pretty good. So here's a nice picture of the telescope at sunset. I don't know if we can dim the lights at all to make some of these pictures a little better. But so here's a picture of the telescope at night, and these are just some images of from the survey. Here's a picture of M51, famous Whirlpool galaxy. These are entirely not random pictures of the sky, right? This is a picture of a globular cluster M13. Here's an interacting pair of galaxies, NGC 5257. The numbers, of course, don't mean anything, but right. But nice picture of the interactions. Here's a little cluster of galaxies starting to come together. And if we have any chance of dimming the lights, I can go through these again if we ever do figure it out. But it's really these ones up in front. There's lights right here, which is the problem. We'll get all the other lights. Okay, so this led to our last, that's getting better, okay. This led to our last big data release. This is a picture of the Northern Galactic Cap. And so that's just, a big chunk of the sky, about a fifth of the sky. And what's happened here is actually all the stars have been plucked out of the images, and all that's been left is the light from the galaxies. So you can actually start to see the large-scale structure just from the distribution of light in this picture. Better yet, thank you. Here's a picture of the South Galactic Cap, just the various pieces of the survey. And so this was actually released to the public in January 2010. It's a total of about 1/3 of the sky. And it's important to remember just how much dynamic range is actually in these pictures. So here's these two again, and then just blowing up little pieces of it to really not random parts, but here's blowing up on M33, and again to M33. And then even once you get down to the scale of just a little piece of M33, there's a lot of data, a lot of detail in these pictures. All told, this is actually over a trillion multicolored pixels of the sky. So, we didn't actually have a 1 trillion pixel camera, but we went out and took a picture of the sky and stitched it together to form a trillion pixels. I'll just zoom back so you can see some of the pretty pictures here. So here's M51, M13, this interacting pair of galaxies, and a small cluster of galaxies. Okay, so that gives us a 2-dimensional map, but now we want to go and try to make a 3-dimensional map. And this is a picture, this is the type of plot we make for that, where this is us at the center, and now this has taken some strip of the sky and used the redshift information to infer distance. And you can see at that point that the clustering really starts to stand out. The universe is very clustered. There's lots of density and homogeneities in the universe. So there are these big walls and big voids in the universe that are just hard to see when you're only looking in 2 dimensions. But when you finally look in 3 dimensions, they all start to really pop out. So we want to use spectra to allow us to measure these velocities and infer the distance. So this is actually done with a spectrograph that involves a lot of optical fibers. So there's a plate here, and I brought, Michael Woodvasey was kind enough to bring one over. So this is a plate of the sky, and you may not be able to see the holes in it quite. Yes, very nice. Yes, you can actually just barely, because we have the light, you can see the holes, right? So every one of these holes is a location of a galaxy or a star that we chose to observe in this part of the sky. And then basically what happens is you're plugging in optical fibers into each of these holes, and those optical fibers then run off en masse to a spectrograph that will disperse out the light and allow us to take a spectrum like what I showed you in the early slides. So basically these all get plugged. Here's a picture of a plug plate. And I can pass this around, but I will say that it's pretty heavy. It's not light. So each one of these plates actually goes, so this is a picture of our survey scientist, Kyle Dawson at the University of Utah, standing before one of the plugged plates. Now these are actually all plugged by hand. This is the team that plugs the plates by hand. So they've now plugged of order 2.5 million of these optical fibers after a bad night. It's a little tough, but and then once they're plugged, then you take them off to the telescope and they get installed. Each of those cartridges gets installed right here, and these are then the spectrographs where the light gets dispersed. Now, that's one plate. You need many plates to make the survey. Each one of those plates is about 3 degrees of the sky. So it's just one big chunk of the sky. But the sky is really big. So to even cover a quarter of the sky requires that many plates, about 2,000 plates. So we've been at this for a while. Each one, each plate you observe for about an hour or two until you collect enough signal to noise. And then you discard it because there's, those holes were drilled in very particular locations. You can't reuse reuse it. So we have a gigantic storage shed of, of these plates. Okay, so now let me turn to, back to the subject of the acoustic oscillation. So we're going to use a very particular type of galaxy, which is shown here in this picture of the Perseus cluster. These big elliptical galaxies, they're very luminous, they have very obvious signatures, they're easy to select. And so we go out and we measure these galaxies because we can see them for long distances away. And this is a picture of a nearby cluster where you can really see the detail. Here's a picture of a much fainter cluster. But if you look, you can start to see the excess of little yellow dots there. That's the type of image we're really selecting from, is trying to figure out which of these we want to put a fiber on. And we'll only get to pick about 1 out of every 100 sources that you can see on this image to actually take a spectrum of. So you have, it's a very limited resource you have to be judicious with. So we might have picked that one, for example. Okay, so once you've done that, then you can make this sample. And this is, again, a diagram of the clustering galaxies where we're down here. But this is now stretching out for a very large distance, much larger than the diagram I showed you before. So this thing is going out of order 4 billion light years. So it's a very large volume of the universe that we're able to survey. And that's what led to this detection in 2005 of the acoustic oscillations. I think I'm going to skip a little bit here because otherwise we're going to run out of time. So in our latest analysis, we find that there's this very nice peak right where we thought it would be, and this has allowed us to get a precision of about 2% in distance. So we're getting much more and more accurate about our measurements of cosmological distance from this. So that then leads us to SDSS-III, which is the next phase of the SDSS project. SDSS-III will be started operations in summer 2008 and will run until summer 2014. And it has 4 surveys under its umbrella. The one that's really relevant here is the Baryon Oscillation Spectroscopic Survey, which is a big large-scale structure survey aimed at studying dark energy by the use of the acoustic oscillations. And then there's 2 surveys which are studying the Milky Way and a survey that's looking for planets. So there's really 3 different items in there. And the support for the survey has come from the Sloan Foundation, Department of Energy, National Science Foundation, and over 50 member institutions from around the world. And I'm glad to say that Carnegie Mellon is one of those institutions, as is the University of Pittsburgh. So we have a lot of local involvement in this project. But people from around the world, there's about 600 scientists involved in the collaboration. This is at a collaboration meeting we recently had. This is about a quarter of the people involved in the project. So it's been a really great collaboration to work with. Okay, so to look at the Baryon Oscillation Spectroscopic Survey, the intent here is to produce the definitive study of the low redshift acoustic oscillations. And we're basically revisiting the area of the sky that we imaged with SDSS, but now doing spectroscopy that's more ambitious, going fainter, going deeper. And this will result in a very large increase in volume above what we had in SDSS-II, about a factor of 7 improvement over what we had before. And the goal is to get to distances that are good to 1%. Which will really be the first time that's ever happened. So the survey is now just over half complete. We have 1 million spectra in hand. It's really been a wonderful data set to work with. So I'll show you some results that we just published last month. This was based on the first 20 months of data. And this is our sort of coverage in the Northern Galactic Cap. And this data will all be released to the public this summer. But we'll be just using here a portion of the data, about 3,000 square degrees, so about a 1/12 of the sky, and about 250,000 galaxies. So again, we found a very clear signature of the acoustic peak, this very nice increase at 500 million light year scale. And this allowed us to measure the distance out to redshift of 1/2 to 1.7%. So these are really excellent distances. The astronomers spent a lot of the last 50 years arguing about the Hubble constant, which is really arguing about the distance scale in the universe. And the argument was over a factor of 2. So basically, some people would argue for a factor of 2 different. There was very religiously held debates about which of these it was. And we're now actually at a precision of order 2%. It's been a tremendous improvement in the field. This is just to compare the 2 data sets that I've now talked about. Here's the data set at redshift 0.35. Here's the redshift that's at redshift 0.57, and they just line up exactly where you'd expect the vertical offset is not important for this talk. And so they're just in wonderful agreement between the two. OK, so that means that we can actually now start to use this method to map out distance versus redshift, which is what I got into this as talking about. So this is distance and redshift, and you can see these little measurements here on this big sweeping curve. And the remarkable thing about this curve is that this curve is not a fit to the data. It's actually a prediction from the microwave background data, assuming that the universe is flat and has a cosmological constant. I'll describe those two concepts in a minute. But this is a prediction of the simplest cosmological model, and you can see that it goes through the data really wonderfully. So if I take this data and divide out by that curve, then you get to these offsets. So the data is slightly higher, a few percent higher than the prediction, not at any level that's a statistical problem, but it's just a beautiful consistency with this prediction from the microwave background and the test of the standard model. OK, so what can we use to really look at this in more detail? Well, again, we're interested in measuring the dark energy. And so we can ask the question, is the dark energy constant in time? Is the cosmological constant actually constant? As you might expect, the cosmological constant model would predict that the answer is yes. But we would like to ask the question, because other models would not have predicted this. They would have predicted that the energy density would vary. And so this gets parameterized. This is parameter W, which W is -1 is the cosmological constant. And different values of W imply different properties for the dark energy. The other major thing we can test is the curvature of the universe. So in general relativity, the universe has an overall spatial curvature. It might be flat like a sheet of paper, or it might be that the universe is like a sphere. Now, it's a little hard to visualize three-dimensional spheres. We're much better at viewing two-dimensional spheres. So you could imagine that there'd be a ball, and you would be an ant walking on the surface of that ball. And you would be able to tell whether or not the ball, whether or not you were living on the surface of a ball or whether you were living on a sheet of paper by walking out some distance, then doing a big circle and comparing the circumference of your circle to the radius of your circle. And on a flat piece of paper, that ratio better be 2 times pi, the circumference to radius. But on the surface of a ball, you'll get a smaller answer. And in particular, if you walk all the way to the south, from the North Pole to the South Pole, your circumference is 0 despite the fact that you walked a long way. So you can get a good measurement of curvature from that. And so this is actually an old picture from the microwave background, where if you have a universe that's flat, you get patterns. The acoustic oscillation patterns are this size. If they're curved, if it's a sphere, then you get bigger bubbles. If it's an open universe or a hyperbolic universe, then you get these smaller bubbles. And you can basically tell by eye from this picture if the universe is flat or curved, curved like a sphere or curved like an antisphere. And so you can really get wonderful measurements of this. And we can see from this, if I go back to this previous diagram and now add in how the prediction from the microwave background would change if you changed the assumption that went into it. If you say, this was the prediction for a cosmological constant model, but if I now say, oh no, let's make the dark energy vary by some amount, then you get a very sharply different prediction here. And you can see that prediction would not match the data very well. Or you could say, I'm all right with the cosmological constant, but now let me not worry about flatness. Let me not assume the universe was flat. Let me put in a small extra curvature. And that moves things to down here. So very small changes in these cosmological parameters actually make big changes in this plot. And we can see that measuring distances to high precision allows you to get very accurate constraints on what the composition and the curvature of the universe is. I'm just going to skip here. So this is then the test that we're doing. So we can basically test, here's our dark energy parameter. So here's the cosmological constant. Here's spatial curvature. Here's a flat universe. And you can see that the data really overlaps very nicely with this region. The data really drives us back to a universe that's flat and has a cosmological constant, the simplest model we could have. And yet the data is actually getting good enough to exercise very precise tests on this. So we're basically measuring the curvature of the universe to about 0.5%. Okay, in addition to that, we also can use this data to measure the expansion and the density of the universe. There's a famous phrasing from Alan Sandage, a famous cosmologist, who described observational cosmology as a search for two numbers. And he meant the Hubble constant, which is the scale of the universe, and omega matter, which is the density of the universe. And the combination of these data sets actually gives really excellent constraints on these two quantities. We've now measured the Hubble constant to be 70 plus or minus 2 kilometers per second per megaparsec. This is the thing that people were arguing about at the factor of 2 level. There was one camp that said 50 and one camp that said 100. And they were each half right, because the answer is 70. And omega matter, 0.277 plus or minus 0.014. So we're really in an era now where we can measure the density, the expansion, the curvature of the universe, the composition of the universe to great accuracy. It's a wonderful progress in the last 20 years in cosmology. So that brings me back to the cosmological pi diagram here, where this number of 73% is not, is now known to very high accuracy. It's really 73% plus or minus 1.5%. Very, very, very well constrained. So we really have a very concrete, simple, and I think in some ways elegant theory for how the universe works from an age of about 1 second after the Big Bang until today and over a wide range of length scales. And this theory is very predictive. It can make great predictions for the microwave background, for large-scale structure, for the formation of galaxies, for the clustering of quasars. You can do lots and lots of different tests of this theory. And it's really a triumph of the last decade that the picture has been tested and confirmed in so many different ways. And so it provides a very robust base for the study of much of cosmology, that we have this very simple and predictive theory. But of course, the problem is that this theory involves an unknown type of matter and this new force that operates on the largest scales, known as dark energy. And that really presents the opportunity for the next decade of exploring how these things might work. And it's important to remember that we've only just scratched the surface of what's possible. So SDSS has surveyed about 1,000th of the volume of the universe that we could use, surveyed fewer than 1/10,000th of the modes relevant to the acoustic oscillations, and fewer than 1/1,000,000th of the modes that are relevant to probing of the early universe. So there's a gigantic amount of information that's left out there for mapping the universe to discover. We really have only just gotten started. And the data sets that are coming in the next decade are poised to increase our reach on these questions by factors of order of 100. So cosmology has benefited an enormous amount in the last 20 years from just an explosion of data. And that trend is continuing. We really expect to gain another factor of 100. And this should have enormous reach on what we can study in cosmology and galaxy formation. And although really we're at the point where we're measuring the sort of most basic parameters to the percent level, there's really lots more you can do as you get the data to be more and more precise. I've talked today about dark energy. Is the cosmological constant really constant? If not, what is it? But we can study things about dark matter. We can look for deviations from the classical cold dark matter prediction. We can look for properties of inflation, the earliest universe. We can look for what the mass of the neutrinos might be. We can look for particles that might have decayed, long-lived particles that might have decayed at some point in the past in the universe. So there's just a ton of things that you can do once you have very precise cosmological data. For the graduate students in the audience, in case there are any, I thought I'd point out that we wrote up a gigantic review article on this recently. So it's here on arXiv, and just a major review of all the different probes of dark energy. So if you're looking for a more technical introduction to the subject, this would actually be a pretty good place to start. So let me conclude. Acoustic oscillations are providing a very robust way to measure the cosmological distance scale. There's very simple physics from the early universe that leaves a clean signature in the clustering of galaxies. And it's developed into a very important tool for how we study the cosmological expansion history and hence dark energy. With SDSS, Sloan Digital Sky Survey, we've used the acoustic peak to measure the distance out to redshifts of 0.35 and 0.57 to better than 2%. It's the best extragalactic distances that have yet been measured, and they provide excellent consistency with the flat cosmology and a cosmological constant. So a very simple model for how the universe might work. We find very accurate measurements for the Hubble constant and the density of the universe. But this is really just the tip of the iceberg. There's tons of data coming down the pike in the next 10 years, lots of people who are eager to figure out what it might mean, and I think lots of opportunities to probe physics in new and interesting ways. So thank you very much for your time.
For the first microwave background picture, you had a uniform cluster disk. Where the next one said it was a redshift, right from our observation. What's our relative speed?
It's about 300 kilometers per second, but maybe it's 600 kilometers per second. It's that range. I think it's 2 parts in 1,000 of the speed of light.
You mentioned the cosmological constant, but you didn't tell us what value it has.
So it's at point, well, in the units that we use, it's 0.73, but that's not probably the units that you want. In terms of density, Leonard actually probably has the number better. It's about, corresponds to about 3 millielectron volts, if that helps. Probably not.
Yes.
So what's the thing that strikes me interesting about the three-dimensional map of the universe? Since you're looking back in time as you're looking further distance, that would seem to do something odd to this shape. If you see what I mean, the expanding universe, you're looking further back in time, so it'd be smaller, and then it's further away. Does that have any odd effect?
Well, you have to compensate for that, but it's actually that's exactly right. I mean, you really, as you go back in the universe, your perception of distance starts to warp, and it's because of the expansion of the universe. So, if you were sitting here in this room, not expanding, everybody's, just standing around, and you go out and you start measuring things, with a surveyor rod or something, you're going to get to a distance system that you are very familiar with, this sort of standard Euclidean distances. But as you go into an if you sort of put the whole room into expanding, all of a sudden things do start to move around on you, and you do have to track for that. And I didn't go into detail on that, but absolutely, if you just go out and you take an object that you know to be a sphere, and you now go out and put it out in the universe, you will actually perceive it to be elliptical because of this shearing, and that's an important opportunity. It's a well understood opportunity in the sense that it's a bookkeeping issue. You can do it, but it actually is an important opportunity.
Okay.
So we told us something today about the shortest correlation length. What could we learn from what looks like a fractal longer lengths? And why are we looking at this?
Okay, well actually, so most of the correlations I talk about are actually the large scales. It's actually the small scales that get to be stronger. So the universe is very clustered on small scales. And the word fractal has various interpretations that I think one wants to be careful about. But yes, there's very strong correlations on small scales. And that's very important. It's telling us about the physics of galaxy formation. It's telling us about the physics of the gravitational collapse into what's called dark matter halos. So literally what the endpoint of these runaway gravitational collapses are. So there's a lot of the story of astrophysics is down on those small scales and trying to understand those correlations. One of the advantages of the acoustic oscillations is that they're out far enough that we don't have to worry about the details of that story because that story is really complicated. So it's really the large-scale aspects that make it so much simpler.
I noticed on a lot of the charts where you showed the agreement between the predicted decline and the actual observation points, that about halfway from where the main hump was that you pointed out, and the right side of the chart, there seemed to be a place where you consistently deviated from prediction.
Right.
And I want to know if that deviation is real, and if so, what is it?
Okay, so we don't actually think that there's any statistically significant deviations from the line. Now, I appreciate that the curves that I show make it hard to see that, and it's because the error bars are necessarily correlated on these plots, and so you have to go in and really do the statistics properly. When you do that, there doesn't actually seem to be any statistically significant deviations from the line. People have worried a lot about that, exactly because it would be something new if you could go out and find it. And on the largest scales, going out beyond 500 million light years, out towards 1 billion light years, then in particular people are worried about, oh, are we seeing some deviation here? And I personally think the answer is still no, but it's definitely something people are looking at very carefully because it would be important if it were there.
One more.
So I noticed that you never used the term black holes even once in the talk. And I'm just wondering if the mass that is contained in black holes at the center of galaxies, does that play any role in this whole picture?
So the black holes that are in the center of galaxies are a very small fraction of the mass of the galaxy, and the galaxies themselves are a very small fraction of the mass of everything that we care about. So it turns out they're not actually a big story for that. What is possible, and people have spent a lot of time trying to investigate, is that maybe the dark matter, and here I'm not talking about the dark matter, not the dark energy, but the dark matter, perhaps it's not some new subatomic particle, perhaps it's actually black holes, and you can pick the mass of the black hole that you would want, but, and people then do searches to try to figure out if they can exclude some of those possibilities. And the answer is that they've actually made a lot of progress on that. So if the black holes are of order the mass of the sun, which you would think would be an interesting choice because stars do form, and when they die, sometimes they form black holes, and so you would think, oh, maybe it could be there. But that possibility actually can be pretty well ruled out at this point. So you just have this question of what mass black hole might it be. But masses that are much lighter than the sun, or even much lighter than the Earth, actually are still possible. These black holes would be sufficiently rare that we wouldn't have encountered one yet, and yeah, so they could be a story on the dark matter side of things.
Thank you again.
Thank you.